everybody, this is Dr. Nigro with a Physics Fundamentals screencast. This one's looking at how we graph motion. All right, there's a separate screencast that deals with position versus time and velocity versus time graphs for our 7 different types of motion. No motion, forward with constant velocity, backwards at constant velocity, and then forwards and backwards speeding up, and then forwards and backwards slowing down. That video does not include information about acceleration plots or how the area underneath some of these curves also gives us some information. So this screencast's goal is to add in that information. All right. So we're going to start by talking about what the different graphs tell us in terms of area and slope. All right. I love this little figure. It shows you a position versus time, velocity versus time, and acceleration versus time plots of a particular motion. All right. And if we look at this particular motion, we can see that we start close to the detector and move away. So that tells me that this object is moving forward. All right, which means that the velocity values are going to be positive. All right, if we look over on our velocity graph, they're all above the 0 line. So velocity is positive. All right, if you look at that position versus time graph, you can see that initially it's pretty steep and then it flattens out. So that shape tells me that the velocities change, the position's changing a lot initially and then changes less and less and less. So that's an indicator of slowing down. All right. And if we look over at our velocity graph, that holds, right? Our velocity values are initially high and then they decrease over time. All right. So that also tells us that we're slowing down. All right. If your velocity value is positive, but you're slowing, then that means my acceleration value has to be negative. They need to be working against each other. And if I look at my acceleration graph, that is the case. The acceleration value is negative. All right, so these 3 graphs show us an object moving forward, but slowing down. All right, now what other information can we get? All right, well, the position versus time graph is curved. So we're not going to talk about area or slope with this curve. All right, now we could find the area under the curve, but we're not going to be doing integrals or derivatives, okay? Instead, we're going to move to our plots that have straight lines. So we've got our velocity versus time plot, and I could determine the slope, all right? And that slope value is going to tell me the acceleration, all right? Now, the other thing I can do with this plot is determine the area under this curve, all right? And if I determine that area, all right, that's going to tell me the change in position of that object. All right. If you think about area in this case, the area is going to be equal to the velocity times time. All right. And that velocity times time is going to give us that change in position. Because remember, velocity equals change in position divided by time. So if I multiply the time over, I end up right here. All right, so the area under the curve of a velocity versus time plot is going to tell us the change in position of that object. All right, now if I go look at my acceleration plot, all right, this is a straight line, all right, the slope here is 0. All right, so we're not going to use the slope here for anything. All right, but I can determine the area underneath this curve. All right, and that area value is going to tell me the change in velocity. All right, so again, that area is equal to acceleration times time. And I know that acceleration is not change in position, sorry, is change in velocity over time. All right, so if I multiply time by both sides, I end up right back here. So that area is the change in velocity. All right, now one thing I should mention, back on the position versus time graph. All right, this particular example we can't use because it's curved. But if instead it looked like this, which would tell us that the velocity was constant, then I could determine the slope. And that slope value would tell me the velocity of that object. All right, so the position versus time graph's slope will tell me the velocity. All right, for the velocity versus time graph, the slope will tell me the acceleration. The area will tell me the change in position. For an acceleration graph, because we're dealing with constant acceleration, the slope will be 0, so it doesn't tell us anything. All right, but the area under the curve will tell us that change in velocity. All right, so these are some things, other pieces of information that we can get. All right, now I did want to take just a moment and talk about the acceleration graphs. All right, now because we are using or working under constant acceleration conditions, all right, it's going to be pretty straightforward for us. All right, if we have no motion or an object with constant velocity, then the acceleration graphs are going to look the same. All right, this is going to be my acceleration on the y-axis, and then time would be here. All right, our acceleration would be 0 because it's either not moving or it has constant velocity, so it is not accelerating. All right, so that one's pretty straightforward. All right, now let's look at what happens if we do have some changing velocity. All right, and we're going to specifically look up if the object is speeding up. All right, so here's our condition. All right, remember, if you're speeding up, then the signs of velocity and acceleration must match. All right, so what does that mean? Well, let's draw our two axes. We're going to include velocity here and time. Then over here, I'm going to do acceleration and time. All right, so let's say that we have an object that is moving forward and speeding up. So the object's moving forward, so we've got velocity values that are positive. And if the signs have to match, that means the acceleration must also be positive. So we would see a matching acceleration plot that looks like that, all right, where the value of the intercept over here equals the slope of our velocity versus time plot. All right, now if instead we're speeding up but moving backwards, all right, then we'll have our velocity values below the 0 line, indicating they're negative, all right, and our acceleration value should also be negative. All right, the units, again, the signs need to match so that we indicate speeding up. All right, the value of acceleration will be equal to the slope for our position versus time graph. All right, so this is what our graphs would look like for speeding up. All right, now let's try one where we're going to be slowing down. Okay, now if you're slowing down, remember the signs of velocity and acceleration must now be opposite of each other. They're working against each other, and then that slows our object down. All right, so I'm going to stack these this time. So velocity and time, and then acceleration and time. All right, so if we start with an object that's moving forward, but slowing down, it's going to have positive values, but the velocity starts high and goes low. All right, so we'll have positive velocity values, but if we take the slope of that, it's going to give us a negative value, which is reasonable because the sign of acceleration should be the opposite of velocity, so we get negative values. All right, if instead the object is moving backwards, the velocity values are negative, and if we take the slope, we're going to find that that slope value is actually positive. So it will look like this. All right. So in this case, our signs are working against each other, which means the object will be slowing down. All right. So this is what the acceleration graphs would look like that would go along with our position and velocity graphs that we talked about in the other screencast. Okay. If you have any questions, please let me know.